All right, let's dive right in. You know how we usually learn linear regression first and then eventually move on to logistic regression, treating them like they're totally separate algorithms? Well, in this explainer, we're going to pop the hood and discover how these distinct machine learning models you already know and use are actually just different flavors of one elegant, overarching framework. We're looking for the unified engine that drives them all.
So think about this for a second. What do predicting house prices and detecting spam actually have in common? I mean, on the surface, absolutely nothing, right? One's a regression task dealing with continuous numbers, the other's a binary classification task dealing with discrete yes or no categories. But while they seem like vastly different tasks that should require completely different algorithms, they actually rely on the exact same master key.
And that master key is what we call Generalized Linear Models, or GLMs. Basically, a GLM is a broad family of models that unifies these distinct classification and regression methods right under a single mathematical framework. The absolute crucial takeaway here is that GLMs take models like ordinary least squares and logistic regression and reveal that they're really just special cases of this much broader unified family.
Our roadmap for this explainer is pretty straightforward. First, we'll hit the grand unified theory. Then we'll unpack the exponential family, followed by constructing a GLM. After that, we'll reveal the universal update rule, and finally, we'll wrap the whole thing up with some graphical intuition.
Okay, part 1, the grand unified theory, the illusion of complexity.
You already know that in machine learning, your task dictates your data distribution. Predicting house prices, you're going to model your output as a Gaussian distribution. Building a spam filter, that's a Bernoulli distribution. Or say you're estimating the number of customers walking into a store in a given hour. You'd use a Poisson distribution for that count data. But here is the wild part. Despite these tasks appearing so incredibly different, real numbers versus binary classes versus integer counts, they literally all use the exact same underlying architecture. Every single one of them is a member of something called the exponential family.
Which brings us to part 2, the exponential family, the mathematical engine. Now this equation right here, this is the heart of the matter. I know, it might look a bit intimidating at first glance, but it's really just the generalized probability density function for the entire exponential family. Basically, if a class of distributions can be algebraically massaged into this exact form, boom, it belongs to the family.
Let's actually demystify this and break it down into its core components. First up, we've got the natural parameter, denoted by eta. That's the core parameter of the distribution. Next is the sufficient statistic, T of y, which, honestly, for our purposes, is usually just the data y itself. Then we have the base measure, B of y. And finally, the log partition function, A of eta. Now that last piece is super important because it acts as a normalization constant, making sure the entire probability distribution integrates perfectly to 1. By isolating these interchangeable engine parts, we can just swap in different values to easily generate a Gaussian, a Bernoulli, or a Poisson distribution programmatically. Now you might be wondering, why go through all this algebraic gymnastics? Well, it's because the exponential family comes packed with some incredibly desirable mathematical properties. Whether you're maximizing likelihood or minimizing loss, these properties guarantee you're going to find the single global optimum. Because maximum likelihood estimation is strictly concave and negative log likelihood is strictly convex, your optimization algorithm is never going to get stuck in local maxima or minima. Translated into plain English, it's a mathematically guaranteed clear path to the best possible model. You will always hit the bottom of the bowl.
Moving on to part 3, constructing a GLM, the recipe for unity.
So how do we actually transform an exponential family distribution into a GLM? We just make 3 specific design choices. Step 1, we assume our target variable y, given the input x, follows an exponential family distribution parameterized by eta. Step 2, we decide that the natural parameter, eta, and the inputs x are related completely linearly, meaning eta simply equals theta transpose times x. And step 3, our model is going to output the expected mean of the distribution. These 3 elegant little design choices let us tie the learnable linear model, which is kind of like the chassis of a car, directly to our interchangeable exponential engine.
Because of those choices, we end up constantly translating between 3 different parameter spaces. To map this out mathematically, we start by learning the model parameter, theta, during training. Then, we use that linear connection we just set up to find the natural parameter, eta. And finally, we apply what's called a canonical response function to get our specific canonical parameter, like phi for Bernoulli or mu for a Gaussian. The absolute best part here is that we only ever need to train theta. Everything else just flows mechanically right from that one parameter.
All right, part 4, the universal update rule. The beauty of GLMs.
The beauty with GLMs is that no matter your choice of exponential family distribution, the update rule remains the same. Just think about the massive implications of that statement for a second. This right here is your ultimate reward for navigating all that heavy math. You literally don't need to derive new gradients for every single model you build.
Whether you're using linear regression, logistic regression, or Poisson regression, the gradient ascent update rule looks exactly like this. It is basically the mic drop equation of machine learning. You just initialize your parameter theta randomly, plug in the appropriate hypothesis function for your specific distribution, so like an identity function for Gaussian or a sigmoid function for Bernoulli, and you can start learning immediately using this one universal rule. The math just seamlessly takes care of the rest for you.
Finally, part 5, graphical intuition, visualizing the math.
Okay, let's picture a graph with your data points. Your linear model theta transpose x is basically drawing a continuous line or hyperplane right through that space. And because of our GLM design choices, this hyperplane directly equals our natural parameter eta. In Gaussian regression, eta is literally the mean or mu of the distribution. So essentially, for regression, our linear model is just trying to string together the center points of an infinite number of Gaussian distributions, tweaking the line until those distributions are perfectly centered over our actual observed data.
Now, what about binary classification? Well, we still learn the natural parameter eta as a linear line. But our target isn't a continuous number anymore. It's just a 0 or a 1. So we pass that linear line through our canonical response function, in this case, the sigmoid function, to map eta to our mean, phi. And this is a brilliant illustration of how binary classification works. We're just wrapping our linear model in a sigmoid function to compress an infinite space of numbers into a really clean, elegant probability curve that always sits perfectly between 0 and 1.
But, what happens when we want to classify more than just two things? Like, what if we're sorting shapes into circles, squares, or triangles? Doing that requires generalizing logistic regression into what we call Softmax Regression, which is modeled using a multinomial distribution. Now we're learning a separate set of parameters, and therefore a separate linear decision boundary for every single class.
To actually make sense of all these competing decision boundaries, we do two things. First, we exponentiate the raw outputs, the logits, just to ensure they're all positive numbers. Second, we divide them by the sum of all outputs, and that is softmax normalization. It guarantees that no matter what raw numbers our linear models spit out, the final output is always a perfect probability distribution that neatly sums up to exactly 100%. During training, we minimize the cross-entropy, which is really just a fancy mathematical way of forcing our model's predicted probabilities to perfectly match reality.
So we've seen how linear regression, logistic regression, and even multi-class softmax regression all emerge from the exact same mathematical engine, which leads us to a pretty fascinating question. If these basic machine learning models are just the exact same mathematical engine wearing different masks, what other incredibly complex AI systems out there are really just simple GLMs in disguise? I mean, deep neural networks, for example, often use these exact same principles right at their output layers. It's a fun, provocative thought to leave you with. Hopefully, this explainer has given you the foundational intuition you need to start spotting these unified patterns out in the wild.